In Chapter 5, Section 2, we'll look at the definite integral, which we'll build on towards the conclusion of Calculus 1. So let's look at problem 1. It says, write the sum using sigma notation. So we have 2 plus 4 plus 6 plus dot, 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 plus 60. So this is called an arithmetic sequence. Arithmetic sequence. Now we usually teach these first in college algebra, so you've probably seen this before. And basically we know it's arithmetic because it goes up by a common addition. So these are all going up by 2. So this has been added 2 to it, 2 to it, and then the pattern continues. So I'm adding 2 every time. And this number is called A1, the starting value, and this number is called AN, the stopping value. And we can see from an equation that AN, so the problem with this one is we don't know what N is. We have to find that. So AN is given to be A1 plus n minus 1 times d, where d is equal to the common difference. And you can find d by subtracting any two numbers in the sequence, later numbers first, then previous numbers. So 4 minus 2, or we can do 6 minus 4, and we both get 2, which we already kind of could tell. So the common difference in this problem is 2. So we plug in what we know. We know AN is 60. We know A1 is 2. We don't know N. We know D is also 2. So we subtract 2 from both sides and get 58 equals 2 times n minus 1, switching the order on those just so we can see it a little easier. Divide both sides by 2 and we get n minus 1. Add 1 to both sides, and we see that n is 30. Now we have to put what represents these numbers. Well, these numbers are just doubling in effect. You're just taking, if k is 1, you get 2, but then you're doubling that, so this is just 2k. So when k is 1, you get that, plus when k is 2, plus when k is 3, plus when k is 4, plus dot, dot, dot. We know k should go all the way up to n, which is 30. So we're going to get 2, 4, 6, 8, all the way to 60. So just like they showed us, 2k should map that arithmetic sequence. Okay, and that's problem 1. Okay, problem 2 is what we call a geometric sequence because, well, it's not quite what we would call a geometric sequence. A geometric sequence has a common multiple. So in the previous problem, arithmetic, it had a common addition, a common difference, adding 2 each time. In this one, it's a nonlinear. So we have clearly each number is being squared. So the function's pretty simple. It's just k squared, where k starts at 1 and it stops at 12. So I guess there's really nothing to show here. We just know that this is n, so we write n is 12. It starts at 1, and clearly each of these numbers is being squared. So I guess there's not much to talk about on that one. Okay, here we go. This one's going to require a little more work. So problem 3, although we saw one just like this in the previous section. So we have k equals 1 to n equals 8 of 2 to the k minus 1. Now I showed us the shorthand, the closed form solution of this particular one in the last section was r to the n minus 1 over r minus 1. Where this is r and n is 8. So this is just 2 to the 8th minus 1 over 2 minus 1. 2 to the 8th minus 1 is 256 minus 1 over 2 minus 1 is 1. The answer to this is 255. So again, if we have that shorthand formula, this right here, that really makes our life easy. Otherwise, you have to take 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus 2 to the 3, all the way up to 2 to the 7th. Can be a lot of work. Okay, let's look at problem 4. So this says, what's the limit? Express the limit as a definite integral on the given given interval. So it turns out that if I have the limit as n approaches infinity of the summation of I equals 1 to n of some function of xi times delta x, that can be written as what we call the definite integral from a to b of the function times dx. So what have we done here? This says that we are letting n go to infinity. N is the number of rectangles we're using to estimate the curve. Number of rectangles. Used to estimate area under the curve. So we had seen a problem in the last section where we had this. We had this curve, I think it was a car stopping in a certain distance or something like that. And it looks like that. Well, we can come up with, we could estimate this with 1, 2, 3, 4, 5 rectangles, and we'll get an area, and it'll be okay, but there's going to be a lot of error, because anytime we have a gap like this, that, and that's all error. So we have underestimated the actual area under the curve because we have those gaps, right? So what we want to do is take more rectangles. So we're going to say, okay, let's take double the rectangles. So we get 1, 2, 3, 4, 6, 7, 8, 9, 10. And it's kind of hard to see, but these gaps will have shrunk. And then you say, okay, well, I'm going to take even more. So we took 5, then 10. Let me take 20. Let me take 40. Let me take 80 rectangles underneath this thing. And what you can imagine is the upper extreme of this is, let's take infinite rectangles. So basically, we get the area under the curve is literally just a bunch of, my pen's probably not going to work with me here, a bunch of straight lines that have almost no width at all, infinitesimally small width, and that is going to be the area. So this is like the number of rectangles equals infinity, and their width, delta x, will become, we'll call it dx, which means a really tiny width. So this dx means a really tiny width. It's literally infinitesimally small width, like just the width of this pencil right here, of this ink. Okay, so where this one had n was 5, and then n was 10, etc. Now n is infinity. We're packing as many rectangles underneath this curve as possible. When we do that, when we pack an infinite number of rectangles, we say that this is an integral. So we are taking the integral of the function times this tiny, tiny width. And again, the function is the height of each of these rectangles. So back here, each of these rectangles, that's the height of x, what rectangle is that? X2. And this right here was the height at x1. And this one right here was the height at x3. Well, it's really, really hard to draw here because here's f of x1. And then right next to it is f of x2. And then right next to that is f of x3. So I just keep packing tons and tons of rectangles. I basically get every one of these heights here. Okay, so this is how we go from a summation, which is a finite, a discrete value. There's only so many n's I pick, and we've seen problems like that, where we did 5 rectangles, or 10, or 8, or whatever it was, or 6. This is infinite rectangles. So we have this symbol here, this integral symbol. And we're going to learn some neat tricks to use this notation where we can avoid these summation formulas, which can be tedious, and with a few rules for integrals, we can quickly come up with the exact area without error of this curve, the area under that blue curve. Okay, so that's the goal. Now the only thing we have to do in this first problem is basically we don't have to deal with xi's anymore. So if it says 8xi3, that just becomes 8x to the third. If it's minus 4xi, it's now just 4x, because these are now definite values, not estimated, not approximate values. And delta x is going to become dx. And then a is 2 and b is 5. Those go on what we call the lower limit and the upper limit of the integral. So that's how you would set it up. You can map this summation directly to the integral with doing it this way. Okay, so let's take a look at problem. More to come on that. We're not done talking about that. We're going to see that in action, and we'll do some calculations with it in the coming sections before the end of the course. Okay, now problem 5. We're going to practice using this definite integral stuff, but we're not going to show you exactly how we're calculating the integral. Instead, we're going to use things that look alike and do a few just algebra manipulations to get the answer. So problem 5 says if you have e to the x times dx, this is equal to e to the 3 minus e to the 1. So basically we have the exponential curve from 1 to 3. The exponential curve starts at 1 and it quickly rises up like that. So we are finding the area between 1 and 3, and we're finding an infinite number of rectangles underneath this, so we're getting this exact area. That is what this is saying. And the answer is right here. Okay, so then it says using that result, find the integral from 1 to 3 of 3e to the x plus 4 dx. Well, there is many useful things about integrals, definite integrals, and that is if I have a to b of a constant times my function times d of x, we can pull the function out of the integral and just evaluate the integral and then multiply by that constant. So we are going to use that, and we're going to pull out that 3. E to the x plus 4 dx. Now we're going to use another algebra shortcut that's not really has to do with calculus at all. And that says if I have x to the n times x to the m, that equals x to the n plus m. But we're going to go this way. So e to the x plus 4 is the same as e to the 4th times e to the x. So we went this way. So we took two powers being added and broke them into two bases with those two powers alone being multiplied. So when you multiply a common base, you add the powers. Now e to the fourth is a constant, so we can pull that out. So we get 3e to the fourth, the integral from 1 to 3 of e to the x dx. And now these look exactly the same, ex dx, ex dx, so I can replace that with this, which is just a number. You can get it on your calculator. So this is going to be 3e to the fourth times, replace everything, the integral symbol, the 1, the 3, the ex, the dx, with e to the third minus e to the 1. And we're going to distribute this into both terms. So we'll get 3e to the fourth, e to the third, minus 3e to the fourth, e to the 1. And now we're going to go this way. These two separate e's can be combined into e to the 4 plus 3. These two e's can be combined to 4 plus 1. So we get 3e to the 7th minus 3e to the 5th. And that is just some number. And it represents the area under this other curve. So this is a different curve. It looks a little like this blue curve with the green area I drew, but it's a little steeper, and it starts at 3 instead of 1. Actually, I can draw this. So this new curve starts at 3, and it's going to be a lot steeper. So it's going to go something like this. It rises faster, and the area under this thing is going to go from 1 to 3. Drew it too steep. So it's going to be this whole area here. And that area is represented by this number, whatever it is. Okay, and that would be problem 5. And actually, as I'm looking at this, it's a little bit different than what I drew, but that's the idea. So it's actually shifted because of that plus 4. But for all intents and purposes, it's similar to that shape. Okay, for problem 5. Okay, problem 6 is going to want us to look at a couple integrals and see what we can do. So it says we have from minus 3 to 2 f of x dx plus the integral of 2 to 5 f of x dx minus the integral of minus 3 to 1 minus 1 f of x dx. Well, this is interesting. The function, let's just draw a random function, and we can say, let's do this, minus 3 to 2, and then 2 to 5. So what this is saying is, this first one is saying, I want the area from minus 3 to minus 2 to positive 2. So that is the area 1. Then this one is saying, okay, I want the area from 2 to 5, and we call that A2. Well, we can write that as just one area. So let's write it as just one area, call it A, and let's just go from minus 3 to 5. F of x dx. So we can replace both of these integrals with one called minus 3 to 5 fx dx. And there's another property that says if I have a minus in front, so if I have minus ab f of x dx, that's the same as flipping these limits, b to a f of x dx. So it's like calculating the area going from, we usually calculate these going left to right. This is like going right to left. And if I do that, I'm going to get a negative value because I'm going to end up taking a bigger number subtracted from a smaller number. So what we do is we just flip these limits. So we can take this one here and flip those limits. So this would be changed from a minus to a plus, flip the limits, it would be from -1 to -3 f of x dx. Well, by that same argument, this is going from -1 to -3, so we can write that as, because these match, we can write this as from this limit to this limit, -1 to 5 of just f of x dx. And that's what we have there. So you just have to come up with those new limits using this property and using this idea that I've captured in this picture here, that if you take your function and break it into chunks, as long as they're touching, as long as they're, meeting at a common point, you can just go from the smallest number to the biggest number. So you can combine separate definite integrals for problem 6. Okay, problem 7 is another one where we want to translate a limit as n goes to an infinite number of rectangles of the summation. So we've got a bunch of rectangles starting at 1 going to n, and the width of each rectangle is xi star divided by xi star squared plus 6 all times delta x. And the interval goes from 1 to 7. Well, that's A and that's B. We're going to replace delta x with dx. We're going to replace this with the integral symbol. And we're going to put A here and B here. And then we're going to replace this with the function of x times dx. So let's see what we know. We know A is 1, we know B is 7. The function, all I have to do is replace xi star with x. So this is going to be x over, it's just x squared plus 6 times dx. And that's literally all we have to do. So let's see, we've got 1 to 7, x over x squared plus 6, and then dx. So we're changing these xi's, these individual rectangles, x1, x2, x3, x4, x5, into an infinite number of rectangles where we can drop this notation of I and star and anything else and just call it x. And this is the definite integral, which we will learn how to solve soon. So there's more to come on this, but for now, that is all we're looking to accomplish. Okay, for problem 7, problem 8. Okay, it says evaluate the integral by interpreting it in terms of areas. So in this one, we want to actually draw the picture. So our function, which is the same as y, is equal to 1 minus x. That is a straight line that starts at 1 and it has a slope of -1. So it's going down. In fact, it's going to go down. The first spot it's going to hit the x-axis is at 1. So it's going to go down to here. And we want to go from -8 to 3. So our interval is -8 to 3. So let's put that on the number line, -8 to 3. So this thing, I wish I had a straight edge here. It's going to go through these two dots, down like this, and then up to -8. Now we need to know the heights of these points. So we need that height and we need this height. And let me use a darker color. So when we plug in f of 3, we get 1 minus 3, which is -2. So this one's at -2. That's the dot for that. And then let's plug in f of -8. 1 minus -8, which is 1 plus 8, which is 9. So this one is 9 units high. And the integral, what it represents is the area between the curve and the x-axis. So this gives us two areas, A1 and A2. And these are just triangles. So A1 is equal to 1/2 times the base, which is, it goes from 1 to -8, so it's 1 minus -8. It's basically what is the length of this base. You can maybe see 8 units to the origin, then plus another 1, which would be a total of 9, times the height, which is 9. So A1 is 1/2 times 9 times 9, which is 81/2. Now, it also has a feature where the definite integral will take areas above the x-axis are positive and areas below the x-axis are negative. So A2 is actually going to be negative because it's below the x-axis. Same idea, it's 1/2 times the base, which is 3 minus 1, times the height, which is 2. Now I don't need to use -2 because I already counted for that negative, so it's just going to be 2. Or this is equal to minus 1/2, 3 minus 1 is 2, times the height, which is 2. This would be minus 2. And then we just have to add these together. Add those two areas. So we get 81/2 minus 4/2, which would be 2 with a common denominator of 2, which is 77/2. That would be the area between -8 to 3 of that straight line curve represented by those two triangles for problem 8. Okay, problem 9 is kind of like one we manipulated a little earlier. It says the area under the curve from 0 to 1 of x squared dx equals 1/3. Then it says find from 0 to 1 the area under the curve of 7 minus 6x squared dx. Okay, so this is going to equal the integral. I should write this formula somewhere. Let's write it down here. If you have the integral of f of x plus g of x dx, you can split that up into f of x dx plus antiderivative or integral of g of x dx. And same rules apply, constants can be pulled out, etc. So we're going to write this as 0 to 1 of 7 dx minus integral 0 to 1 6x squared dx. This is equal to 7, bring the 7 out, dx, minus bring the 6 out, 0 to 1 x squared dx. But we know all of that, all of this is just 1/3. So that whole thing is just 1/3. So we're going to get 7 minus 6 times 1/3. But what is this? So the integral of dx is, and actually I almost want to put the 7 back inside here. What would be the integral from 0 to 1 of 7 dx? The function is the constant 7. So in a picture, that is a graph that has a height of 7. And it's a horizontal line that goes from 0 to 1. So this is the horizontal line. And the area goes from 0 to 1. This would be the area. Well, that area is super easy to calculate. It's the width, which is 1 minus 0, times the height, which is 7, which is just 1 times 7, which is 7. So antiderivatives of constants are just areas of rectangles. And so this area is 7 minus the 6 times the 3rd, 6 times a third is 2. 7 minus 2 is 5. So the area underneath that more complicated curve is 5 based on just knowing this and being able to split up the integrals and being able to pull constants out of integrals, and then knowing that a constant is just going to be the area of a rectangle for problem 9. Last problem in this section, very similar to what we just looked at. So we have two integrals that they give us, from 0 to 5, f of x dx. They tell us, don't know what the curve looks like, but we know from 0 to 5 the area under that curve is 35. Then they tell us from 0 to 5 of g of x dx. Don't know the curve, but we know the area under it is 12. So then they want us to find from 0 to 5 of 2f of x plus 4g of x dx. Well, just like before, we can split this into 2f of x dx plus the integral symbol goes on both of these, 4g of x dx. So this is that formula I wrote in the last problem. You can split these addition problems up. Then we're going to pull the constants out front. And then and only then can I replace fx dx with 35. And all of this, the integral gx dx, all that with 12. So it becomes a pretty simple problem now. It's just 2 times 35 plus symbol, 4 drops down, times 12. And that's going to be 70 plus 48, which is equal to 118. Okay, and that is a nice introduction to definite integrals, areas under the curve, draw the curve, try to estimate. If it's simple, like a rectangle triangle, we can use geometry to solve the area. As we get more complicated, and we will see some other techniques to actually get these numbers. But for now, that will do it for section 5.2.